So in Chapter 8, what we'll start out by is assigning a problem set. That would be problems 8.1, 8.4, 8.5, and 8.6. 8.4 is a little bit, it's kind of long. Make sure you read carefully what it's asking you before you do some of the problems. It's sometimes a little confusing. So if you don't understand exactly what they're asking, you might want to come talk to me about it. So what we're going to talk about in this chapter is it's actually quite a long chapter because it goes through the derivations of all these methods and how to deal with the convective processes. We're going to skip most of the derivation process and just give you some of the results. And that's for time reasons, and also a lot of my students are using convective methods, and if you're using them, you really have to do it yourself. You can't just think about it. You actually have to do some of those methods. So I would suggest, if you're interested in doing some hydrodynamic methods, go back and look at those equations and work through them. You've got a lot of the skills you need at this point, I think, to work through most of those problems. So what we're going to do in here is, as I said, try to increase the rate of mass transfer by stirring the solution somehow. And there's a couple different ways that people have proposed and used to stir solutions. One is taking electrodes of increasing complexity, starting out with a fairly simple one, where you can take this would be a glass rod, and having sticking out of the glass rod a wire, a stiff wire. So this would be platinum or whatever sort of electrode material that you'd like to use. And you just rotate this glass rod out at whatever revolutions per second you like. And that, as that wire stirs, rotates around, it stirs the solution. And you can see that the diffusion layer that's formed is going to be continuously sheared off, and a fresh new diffusion layer. So you will increase the rate of mass transport. A related idea to that, a little bit more sophisticated way, is to do what they call a rotating disc electrode, where you'd have some embedded electrode material in a smooth, flat surface in some sort of shroud, and that would be, say, glass or Teflon, some sort of polymer, typically, and maybe platinum electrode, carbon, gold, silver. And again, you would rotate that rotating disc and cause the mass transport rate to increase. It's a little bit easier to analytically and theoretically derive expressions for this rotating disc, so it actually is a more popular method. Vibrating wires are also used. Not so much anymore. People have really not used a lot of these kind of easy to make electrodes, because it turns out you can use other sorts of things that are commercially available that give you much more reproducible results. The vibrating wire would be one example, where you would just say, take a wire sticking out vertically from a system and then rotate it, vibrate it back and forth with, say a cone of a speaker or something like that would be a typical way. Another kind of electrode is kind of a messy one and not so environmentally friendly, is this one here, where you take a solution, a bath of solution, and like a mercury drop electrode, you have a capillary filled with mercury, but you have at the end of that capillary a little nozzle. And the mercury under pressure, gravitational pressure, will squirt out of that nozzle and form a stream, which then will break into drops as it goes out of the solution. So you've got a stream of mercury flowing through the nozzle, going through the solution, and then emerging from the solution, and then disconnecting electrically. So you have an electrical contact all through that stream of mercury. And of course at the bottom you'd have a mercury pool. And this is streaming mercury electrode. Obviously a little bit not non-politically correct anymore to have this much mercury, especially jets of mercury streaming out, but people still use it a little bit. Another very popular method is to use porous electrodes with a solution flow through somehow, and these would be useful for detectors and also for useful with synthesis type applications, where you want to do an electrosynthesis, so you want a high surface area and you want to move your material through in a constant flux. So you'd have some sort of porous material, either beads of material, packed into a column, say. And if you pack those beads so that they're touching, they'll all act as one, but there'll be a nice network, a high surface area there. Another way to do this is to use carbon fiber mats. You can actually get carbon fibers that are woven into fabric or into a sort of bags of carbon fiber, hairball if you like. And those also will work reasonably well. You can also buy what they call vitreous reticulated vitreous carbon, which is like glassy carbon, which some of you might have experience with, but it's foamed into so it looks like a porous carbon electrode, and those are very useful too. So a lot of people use that material, reticulated vitreous carbon, as flow-through electrodes, especially for synthetic purposes. Another type of electrode that's actually quite useful is a wall jet electrode. Uses a nozzle, and having that nozzle will then impinge upon an electrode. And you can see from the name, the jet of material escaping from the nozzle will impinge on that wall of the electrode and then exit from the sides, and so you get a continuous bath of material on that electrode. Now, you can either have this happen once or you can recirculate this and so on. Usually this is a kind of a wasteful method, but it actually gives you very reproducible results, so it's useful in that particular case. Sometimes these are set up as detectors, like you can put this on the end of a capillary or chromatography column and act as a detector. Also useful for doing electron transfer kinetic type studies. Those are just a few examples, and if you thought about it, you could probably come up with plenty of other ways to move the electrode or solution past a stationary electrode. Another one that I have in the notes is you could use a tube of some sort, a pipe, and flow the material through that pipe, and if that pipe is an electrode, that can do some stuff for you. Planar electrodes, you can have the electrode acting as a plane, and so the whole electrode can be a plane, or it can be embedded in some other material so that you have an electrode in there. The important thing with these planar electrodes is that you can have flow parallel to the surface. In other words, the flow is flowing across the plane of the electrode in that particular way. That's not used like this so much, but you'll see a lot of times detectors, especially detection systems, having a disc in there, and that would be your electrode as it flows past. And sometimes it's a disc, single disc, sometimes it's a pair of discs. Either a pair can be opposed like so, or they can be serially arranged so that the flow goes over both of them. And by adjusting the potentials for the different electrodes, you can get some different types of detection methods, which we won't talk about right now. And the other one is a planar method, which is similar to the wall jet, but in a more general situation where you just have an electrode and having the flow impinge on that electrode that's placed in a flowing stream. So that in this case the flow is perpendicular, where here the flow is parallel. And so again, as I said, you can come up with all kinds of ideas. The real tricky part is coming up now with a theoretical description of the effect of the flow on the current and response of the electrode. So the analytical methods of solution limit a lot of times whether you're using, for what kind of use you're using these for. Typically for analytical purposes, you really are not that interested necessarily in an exact analytical solution. You'd like it usually, but you can avoid having one if you can do a calibration curve or something like that. Whereas if you're doing this for kinetic studies, you really want to have a good exact description of the current potential kinetic relationship, otherwise you won't be able to treat your data accurately. Now, one of the things about these types of flowing or convective systems that is different than the diffusion-based systems and somewhat reminiscent of our earlier treatments of current potential curves is that they give steady-state currents. So when they give steady-state currents, that often simplifies the analysis of the data. And that's one of the reasons people sometimes use this, is because it simplifies the data that they observe. What do we mean by steady-state current? We mean currents that are independent of time. And so because they're independent of the time of the potential excitation, you get the same sort of current whether you've just started the experiment or whether you're 10 minutes into the experiment. Now that's an approximation, obviously. Always, at some point the current will deviate depending on the time. But generally we can arrange our convective systems to give a nice steady state response. And as I said, that makes it simplify some things. It makes it simple to record the curve because we don't have to have a fancy recording device that has very rapid response times, things like that. So we can use simple recording devices like a strip chart recorder. That makes it easy. Usually also that means that we can minimize the effect of double air charging because we don't have to change the electrode potential rapidly. That means that we don't have large electrode charging currents, or a minimum. So the downside of that is we lose some information about time in the time of the events. And so we make that up by varying some other time-dependent parameter in our experiment. And usually that time-independent parameter is the flow, how rapidly we're moving the material past the electrode surface. So really the trouble, as I said before, is coming up with the analytical expressions or theoretical expressions or simulations of the data. So let's take a quick look at that. Recall our expression for the flux of species J. And if we talk about the vector flux for species J, we would have a couple of different parts to it. One would be a diffusive component. So the diffusion of J, C sub J. And then there would be a migration term dependent on the charge of the species in the system. And the potential, and then a convective term. So generally what we're going to do is we're going to try to minimize or eliminate the migration term, and that's often done, as just as in the diffusion case, by adding large quantities of supporting electrolyte and to remove the possibility of migration. Sometimes it's not entirely possible to do that, but we generally eliminate it as a consideration. So then we have a net vector motion for something in the 3 dimensions with our unit vectors with velocities in oops, that's not that gradient. That's what I meant to write there, was this V bar. And that's what I was confused about there for a second. So we have, of course, the movement of the solution with the velocity in any of 3 directions. We have our unit vectors and the velocity components in each of the 3 directions. So So if we rearrange that, we're going to have our general convective diffusion equation where we have concentration of species J as a function of time is going to be equal to the diffusion term C sub J, that's J, minus the convective term C sub J. Again, just like in the diffusion case, we often restrict ourselves to one dimension or something like that to make it easier on ourselves. So we set up the experiment so that we only have one-dimensional worries. So as always, we use x as that direction. So the movement of species J, concentration gradient of species J as a function of time in one direction is the diffusion thing, the second derivative of the concentration gradient, and the velocity in the x direction and the gradient of the species J. Okay. The problem with this particular equation to solve is we can solve this part, we've already done it, but this part is hard. It's hydrodynamic, and that can often lead to tricky solutions. And so we're not going to really try to become hydrodynamic experts because I'm not one, and it's just too much work for this sort of class. But one method that has been pretty adequately treated